Let's look back at what we said about electric fields last time a little bit more, and then we'll move on to doing some actual problem solving with electric fields. So here is a positive charge that's creating an electric field. Okay, it's just creating an area around it where other charges will experience a force. That's what a field is. So let's just start with a positive charge over here. This little guy we call a test charge. A test charge is just to see what the effect of the larger charge's field is. It doesn't make its own field. That's the big thing about test charges. We consider that they're so small, they don't create their own field. These two charges repel each other, and so we get this kind of line going on. So that would be a force line, but this is also a field line coming from this charge. So a field line just tells you what kind of force positive test charges in the area would experience. So no matter where you'd put a test charge, it would be repelled from this positive central charge. So our field around this positive charge would look like this. It doesn't really matter how many field lines you draw. This is just supposed to be a representation of the force that's happening around this positive charge. So no matter where you'd put a positive charge, even if it's here, between the field lines I drew, it's still going to be experiencing the same force. It's still going to be experiencing this force. It's inside the field, and so the field lines are just there to show you what kind of force would be happening to a positive test charge in the area. Okay, and remember that if we would put a negative test charge in the area, it would just experience the opposite force. Okay, so it would experience a force pulling it in to the field or pulling it into the central charge. But this is not a field line. This is what's happening to the charge. The field lines stay the same. They're drawn as though they were acting on a positive test charge. Okay, so if we were to do the same thing with a negative central charge, let's imagine that we have a positive test charge hanging out here somewhere. These two charges would attract each other. So this positive charge would be pulled in toward the negative charge because they're opposites. And so the field around a negative charge is just pointing inward because all the positive test charges in the region, they would all be pulled inward to this central negative charge. Okay, so this is a diagram of the field around a negative charge, and the other one is the diagram of the field around a positive charge. It's just showing you what would the force be on a positive test charge in the area. And again, one more time, if you would actually put a negative charge in the area, the force it would experience would just be the opposite. Sorry, the opposite compared to the field lines. Okay, it would be repelled because this is a negative charge. Okay, so that's where we started, that's where we left off last time. Now we're going to move on to a few more specific circumstances with electric fields, and then we're going to end off with how do we actually calculate the forces that different charges are experiencing. So we want to start off with this diagram down here. Okay, we've got this in mind. Now, something odd is happening over here. We just drew way up here two charges with only straight field lines pointing inward to it. Okay, that's because a positive test charge in the area would be pulled straight to the center, almost straight to the center of this negative charge. Okay, but if you have multiple charges in the same area creating their own fields, then they interact with each other in sometimes a strange way. So sometimes you'll end up with curves going on. Okay, so remember that an electric field line gives you the direction of the force on a positive charge. Okay, But if you have multiple field lines, let's say they end up curved somehow, in order to figure out the force a charge experiences, you'd have to do a tangent line. Okay, so let's say that you would put a positive charge right over here. Let's make it red. So here's a positive charge right over there, positive. The force it's going to experience over here is going to push it away from this main central positive charge. Okay, but it is experiencing a very small amount of attraction over here as well. Okay, so it's experiencing an attractive force to the negative charge and a repelling force from the positive charge, but the repelling force from the positive charge is much, much larger because it's much, much closer to that positive charge. And so what ends up happening is that we're going to add up these two force vectors because of each charge, and so the total force line would end up being like this. Okay, that's why these field lines are drawn curved like this, because this is telling you the total field right over here. So you've got this straight field coming off of the positive charge, but you've also got a field coming off of the negative charge that it's weak over here, but it is still there. And so they're curved because you're adding up the force lines or the field lines from each charge. And so they end up curved like this. And so if you wanted to know the force on this positive charge at this exact point where it is, you would end up drawing a tangent line to it like that. Okay, we can also do the same thing in another place, let's say over here. Let's say I'm putting a negative charge right there. So this negative charge is experiencing an attractive force this way, and it's experiencing a repelling force this way. And if you add those two force vectors up, you're going to end up with a total force vector. Let's make it a rainbow one. This way. Okay, if you add both of those green vectors up, you're going to end up with just a total of this rainbow force vector. Now, that rainbow force vector is a tangent to the field line that it's on. Okay, and that's the point. The field lines are drawn with all of the fields in the area in mind. They're curved because they're just added up for both of them. Okay, you don't have to really remember how to add up these force lines or these field lines. You just have to remember they end up curved like this. Okay, so these negative charges will attract positive test charges, and that's why they're drawn inward like this, because they attract positive test charges. And these field lines on the positive charge are drawn outward because they would be repelling positive test charges. Okay? So it still follows our field line rules. So the tangent to a curved field line gives the direction of the field at exactly that location. So sometimes you're going to end up with curved fields, and a tangent line will tell you the direction of the field and the direction of the force at exactly that location. Okay, the force on a positive charge is in the same direction as the electric field, because electric fields are drawn in the direction of the force on a positive charge, and the force on a negative charge is just the opposite direction. Okay, and so we've drawn what two different test charges would experience in this field as tangent lines. Okay, so you need to be able to draw those things. You're going to get some practice from that in the homework book. Okay, and we also brought up last time that to calculate the strength of an electric field, you take the electric force, little e down here, you take the electric force and divide it by the charge that's experiencing the field, and that will tell you the strength of the field. Okay, so that comes from this equation. The electric force is equal to QE. This is a vector, this is a vector. Q is charge. It's not a vector, so it has no direction, but it has a polarity. So charge can be either positive or negative, but that doesn't really have anything to do with direction. It just has to do with its polarity. Okay, so this is electric force. And that's in newtons, as all forces. This E over here is the electric field strength. Electric field. And that's usually in newtons per coulomb, but it could be in newtons per EC. Remember that from last time. And this Q over here is charge. And it's usually in coulombs, but could also be in ECs. Now, when you're calculating the charge on an object, you could use this formula. So this is charge equals the number of electrons gained or lost. Number of electrons times this E here is the charge on one electron. And that's in coulombs, so that would always be 1.6 times 10 to the negative 19 coulombs. Okay, so this is really just a way of converting ECs to coulombs. The number of ECs that you have, which is the number of electrons, times the charge on each electron gives you the charge in total in coulombs. Okay, now let's do a couple examples here. Calculate the force on a positive 4 coulomb test charge in an electric field with a strength of 800 newtons per coulomb west. Calculate the force. Okay, and so remember we get the force from that F equals QE formula. F equals QE. So this is force equals charge times field strength, electric field strength. So it tells us the charge that's experiencing the field right there. It tells us the field strength right over here. And so we really just have to multiply those things as long as their units match. So this 0.4 coulombs here matches with the newtons per coulomb here. As long as we're working with coulombs and coulombs, then all we need to do is actually plug them in. No conversion necessary. So the force that this is going to experience is going to be 0.04 coulombs times 800 newtons per coulomb, and that equals 32 newtons. This is a vector, and so it should have a direction on it. So to figure out the direction, we're going to look at the fact that the charge is positive. This is important. Positive test charge, and the field is pointing west. Okay, and remember that fields point in the direction of the force on a positive charge. I'm going to try and pound that into your brain. Fields point in the direction of the force on a positive charge. And so this is a positive charge. The field is pointing west, so that means that our direction is going to be west. So the force is going to match the direction of the field. Example 2. In an electric field with a strength of 4.8 times 10 to the power of 18 newtons per coulomb south, this says times 10 to the power of 18, not 1018, 10 to the power of 18. A charged object feels a force of 12 newtons south. What is the magnitude of the charge on the object? So we're asked to figure out the charge, and we are given the electric force, and we are given the field strength. So we're going to use F equals QE to solve for the charge. And we'll just rearrange it to solve for the Q. So we need to move the E to the other side. So we're going to divide by E and divide by E. And so we'll end up with Q equals force divided by field strength. Let's try that again. Electric force divided by field strength. Okay, so that's Q equals electric force of 12 newtons divided by 4.8 times 10 to the 18 newtons per coulomb. So when we do this division, the newtons will cancel out and we will be left with coulombs. So the charge that we'll get out of this calculation will end up being in coulombs, not in ECs. So 12 divided by that is Q equals 2.5 times 10 to the negative 18 coulombs. Okay, charge has a polarity though, so this either needs to be positive or negative. So when we're figuring out the polarity of the charge, we have to look at what direction is the field strength, or what direction is the field pointing, and what direction is the force pointing. So the field is pointing south, and the force is pointing south. So the field points in the direction of the force on a positive charge. Okay, so a positive charge in this field would experience a south force. And it turns out that the force that's being experienced is a south force. Okay, and so those two things match, which means this must be a positive charge. Okay, because the field points in the direction of the force on a positive charge. Now, if this was a negative charge and the field was pointing south, you would have ended up with a negative force, which would be north, a north force. Okay. How many electrons has this object lost or gained? So now we're taking this charge in coulombs and we're trying to solve for how many electrons is that. And remember that the number of electrons is just the number of ECs. So if you're measuring the charge in ECs, elementary charges, you're getting how many electrons have moved. Okay, so the first thing that we're going to look at is, has this thing lost or gained electrons? So it's a positive charge. And so for something to become positively charged, it must lose negative charges. It's got to lose electrons. Okay, so here's our answer for that part. We have to be losing electrons to get a positive charge. Now, how many electrons has it lost? In order to do that, we're going to take coulombs and just change it to ECs, right? Because that's what the question's actually asking. How many electrons is this? How many ECs is this? So we're going to start with 2.5 times 10 to the negative 18 coulombs, and we're going to do a unit conversion. We had a formula up there, Q equals NE, but that's really just a unit conversion formula. You're taking a charge in coulombs and you're changing it into ECs. So you are welcome to use this formula if you want to, totally fine, but I'm just going to do a unit conversion from coulombs to ECs. So we start with coulombs, which means we need coulombs on the bottom and ECs on the top. 1 coulomb is 6.25 times 10 to the power of 18 ECs. And when you multiply those things, you get 15.625. Okay, so 15.625 ECs. We said last video that ECs have to be measured in whole numbers, because this can't be 15.625 electrons. That doesn't make sense. There's no such thing as 0.625 of an electron. So according to our rule, we round this down. And so our final answer would be 15 electrons lost.